Hello, everyone. Today I will talk about some abstraction techniques for analyzing cyber-physical systems with AI-based controllers. Let me start by giving a brief introduction to formal verification of CPS in the classical setting. We are essentially looking at software that controls certain physical entities, as in a cruise control, where we have software that controls the velocity of the vehicle, or medical devices where software controls the human physiology. On one hand, these systems provide enhanced safety and enable sophisticated functionalities. But on the other hand, they're also deployed in highly safety critical environments where we require them to behave correctly. In fact, software errors or design errors can be catastrophic and lead to billions of dollars in loss. And hence, the grand challenge is how do we build and deploy cyber-physical systems that are reliable? Model-based design has emerged as a promising methodology, wherein you start by modeling the physical system, often as a differential equation, and then the engineer designs the controller and performs some analysis on this closed-loop system. In fact, modern platforms allow one to generate code automatically from this high-level design of the controller. In terms of the analysis, the state of the art is mainly based on simulations, wherein you start the system from some initial state and observe the execution of the system and check if it conforms to an expected behavior. And this is repeated multiple times until you have certain amount of confidence in the correctness of the system. While simulations help in unraveling bugs, they seldom suffice to provide the level of guarantee that is required of these safety critical systems. And that's where formal verification comes into picture. In fact, the aerospace industry recommends doing formal analysis to certify commercial aircraft software today. Formal verification in a nutshell consists of a mathematical model of the system to be analyzed and a mathematical specification that captures the notion of correctness. And then there are verification algorithms which take the model and the spec as input and output that either the model satisfies the spec along with a proof of correctness, or they output a counterexample, which is essentially a software bug. And we're going to discuss all of these components of formal verification in the context of cyber-physical systems. Let us consider an autonomous vehicle along with a controller, which is essentially a lane assistant, whose objective is to keep the vehicle on the lane. On the right, you see the lane depicted as the gray region. Let us consider a very simplistic modeling of this vehicle dynamics. Let x of t denote the horizontal distance of the vehicle from the center of the lane, and let u of t be the input horizontal velocity to the vehicle. Then the dynamics is essentially an update of the horizontal distance based on the horizontal velocity u of t. U of t itself is now given by a controller, which is essentially a state feedback controller that takes as input the current distance of the vehicle and outputs u of t, which is either 0, -1, or 1. If x of t, the distance is between L and R, that is the vehicle is on that in the center of the lane corresponding to that brown region, then the velocity is going to be 0, the horizontal velocity. On the other hand, if x of t is greater than R, that is the vehicle is to the right of the brown region, that is towards the edge of the gray region, then u of t is set to -1, which essentially corresponds to a corrective action to bring the vehicle back towards the center of the lane. Similarly, if x of t is less than R, then u of t is set to 1. The execution of the system can be understood as a lockstep execution between the physical system and the controller. So let's consider the two components separately. Suppose that we start at some point x0, then the controller senses the position and generates an appropriate input velocity u0, which is then fed back to the vehicle dynamics to update its state to x1, which is again sensed by the controller to generate the next input velocity u1. And u1 is now again fed back to the dynamics to update its state to x2. And this process continues. We are interested in ensuring that the vehicle remains on the lane under the influence of the controller, which is essentially a safety specification. We are interested in checking if the system, starting from a given set of initial states, can avoid reaching a set of unsafe states, which is essentially a safety problem. In our case, the set of unsafe states is all those positions of the vehicle which are outside the lane. And the crux of safety verification lies in computing the reach set, which is the set of all those points that can be reached from the initial state by the system. If we can compute this reach set and ensure that the reach set does not intersect with the unsafe states, then we know that the system is safe. In the case of software-controlled physical systems, computing this reach set requires us to also compute those intermediate inputs that are generated by the controller. In particular, we will need to compute two primitive computations: a post-computation of the dynamical system, which essentially corresponds to computing the states that the system can reach given a set of inputs, and the output range analysis problem, which essentially computes all those inputs that are generated by the lane controller or a controller in general, given a set of input states. And then we can iterate over these two operations until a fixed point is reached. While this iterative algorithm is straightforward, there are several intricacies that need to be examined. For instance, computing this post set might not be feasible in an exact sense. Also, the iterative algorithm might not converge in a finite number of steps. So there's a extensive amount of work on exploring these issues in the realm of hybrid systems, which has led to several tools in the last decade or so, which examine different classes of dynamics and different approaches to verification. For instance, SpaceX and Flowstar look at symbolic approaches for linear and nonlinear dynamics. C2E2 is a simulation-based tool. Here examines an abstraction refinement-based approach. Then there are theorem provers like Chimera, and also constraint solving-based tools like Beaver and DReach. Now we have a new genre of cyber physical systems in which we have AI-based controllers. Now that we have these fully autonomous ground and aerial vehicles that operate in highly dynamic and uncertain environments, classic control design methodologies are falling short, and traditional feedback controllers are being replaced by learning-based components such as artificial neural networks. Consider, for instance, the scenario of autonomous driving, wherein the controller receives an image of the environment of the vehicle and uses that to compute the distance to other vehicles as well as obstacles, and also computes the control input. This task of computing the distance to the vehicles from the image can be easily implemented using a neural network. In today's talk, I'm not going to distinguish between perception and control, and I'm going to club them together in this controller component. As another example, consider the ACAS-X system, which is an airborne collision avoidance system that implements a traditional controller, which is essentially a large lookup table, and that is highly inefficient to implement in real time. Hence, there has been some effort to learn a neural network controller, which is the ACAS-XU, that is much more efficient in terms of computation and memory. And we will be using that to illustrate some of the results that I will present later. Coming back to the question of formal verification, the state feedback controller is now replaced by this large and potentially deep neural network. We can try to use a similar framework as before, and the post-computation problem is still being solved on a similar dynamical system, but we need to now compute the output range analysis on this large neural network, which is a highly nonlinear complex function. Hence, existing techniques may not extend to this setting, and even if they extend, they might not scale. And there has been an increasing amount of interest in understanding and studying these kind of output range analysis problems, both for standalone neural networks as well as those that serve as controllers in a larger CPS. And this slide lists some of the recent work, but it is in no way exhaustive. However, it goes to show that there is an increasing amount of interest on this important problem, and it's receiving the much needed attention. Next, let us consider the problem of output range analysis of a neural network. Let me start by giving a brief introduction to neural networks and setting up some notation. Recall that a neural network consists of a set of nodes or neurons that are arranged in layers. The first layer is referred to as the input layer, the last layer as the output layer, and the intermediate layers as the hidden layers. There are edges between adjacent layers which are weighted. There are also biases that are associated with every node. The computation of a neural network proceeds in a layer-by-layer fashion from the input layer all the way to the output layer. More precisely, you start with some values to the input layer, and based on those values, you update the values at the next layer, and so on. The value at a node is computed from the values of the nodes at the previous layer in two steps, the first of which corresponds to a linear transformation, followed by the application of an activation function. Let's look at that in more detail. Let's focus on a particular layer, in fact, a particular node of that layer. The first step corresponds to a linear transformation, which is obtained by adding the bias at that node to the weighted sum of the values at the previous layer, where the weighting is done according to the edge weights. For instance, the value at the node S11 is 1 times the value at the node S01 plus 4 times the value at the node S02, followed by adding 19, which is the bias at this node. More generally, the value at a node S prime is going to be summation over all the S's corresponding to the nodes of the previous layer and adding up the product of the value at that node and the value of the edge joining that node to S prime, and eventually adding the bias at the node S prime. The second step corresponds to applying an activation function, and we're going to look at ReLU functions, that is rectified linear units, which corresponds to applying a function that returns the same value if the value is positive and returns 0 otherwise. For instance, sigma applied to the value of the node S11, which is 28, is going to be just 28 because it's a positive value. And once we have the value of this node, we can compute the other values of the node independently. Note that though we can compute the values of these nodes independently, the values do depend on all of the values of the previous layer. And once we have updated the values of the first layer, we can similarly update the values of the other layers. Next, we formalize the output range analysis problem. Note that for every valuation of the input layer, there is a corresponding valuation of the output layer. The output range analysis problem consists of, given a neural network and a set of valuations for the input layer, compute the corresponding set of valuations for the output layer. Let's discuss a constraint solving based approach to solve the output range analysis problem. It essentially consists of encoding the input-output relation of a neural network as a constraint over variables which represent the values of the different nodes in the neural network. More precisely, we construct a constraint called encoding of XS, where XS is a variable corresponding to the node S in the neural network. And once we have this constraint, we can find the output range by finding the minimum and maximum values of the variable X output, which corresponds to the output node, subject to the constraint of this encoding of XS. Let us consider a mixed integer linear programming based encoding of the input-output relation of the neural network. First, let's focus on encoding a particular layer. Then we can compose the encodings of different layers to obtain the overall encoding of the whole network. First, we'll focus on a particular layer without the ReLU operation. Let Si denote the nodes of layer I, and Si plus 1 denote the nodes at layer I plus 1. Let Bi be the bias associated with layer I plus 1, and Wi be the weights associated with the edges between layer I and I plus 1. Further, let Xs be the variable that represents the value of a node S. Now we can write down the value at any S prime in the layer Si plus 1 to be the sum of the bias at that node S prime and the summation over every S, which is a node of the previous layer, of the product of xs and the weight from s to s prime. Note that this is a linear constraint because the variables that we have here are xs and xs prime, and wi and bi are just constants that come from the network. We will rewrite this linear equation as these two linear inequalities, which will come in handy when we go further. Next, we will consider the encoding with the ReLU function. First, recall that this linear expression corresponds to a linear transformation of the values of the nodes in layer I. And the ReLU function essentially says that we want the value of this variable xs prime to be equal to this linear expression if the value of the linear expression is positive, and we want it to be 0 if the value of the linear expression is 0 or negative. This is typically achieved by a big M encoding scheme, where M is a value that upper bounds the values that any of the nodes in the neural network can take during any execution. The precise encoding is given here. It has this term M times QS, where M is again a constant value and QS is an integer variable that takes values 0 or 1. Now, if the value of this linear expression is positive, this inequality enforces xs prime to also be positive, and that enforces this term to be positive. And this term can only be positive if qs prime is 0. But if qs prime is 0, this term vanishes from these inequalities, and what we get is just this linear expression, which is what we want in the case that this linear expression is positive. Now, if the linear expression is negative, then we note that the value of this term has to be necessarily positive, that is qs has to be 1. And the reason is, if qs is 0, then this inequality basically says that xs has to be negative, because we are considering the case where this linear expression is negative. But xs cannot be negative in any case, xs prime cannot be negative in any case, because it is the value that is obtained by application of the ReLU function, which implies that qs prime has to be 1. But if qs prime is 1, then the value of this term is 0, which forces xs prime to be 0, which is what we want in the case that this linear equation is negative. Note that in order to encode the relation without the ReLU function, we had this linear equation where the variables were all taking real values. But in this particular encoding with the ReLU function, we now also have variables that take integer values. And that's where this mixed integer linear programming becomes necessary. There are several works that consider constraint solving based approaches for solving the output range analysis problem. Here are some of those. Sherlock is a tool based on mixed integer linear programming based encoding. ReLUplex is a SMT solver in which we can encode the input-output relation of a neural network and use that to do safety analysis. Note that these problems are computationally hard problems. They are basically NP-complete problems. And hence, in order to scale up the analysis using these encodings, we need to really make sure that the size of the encoding that we get is small. However, as we saw, the size of the constraints increases proportionally with the size of the network. We saw that the number of variables in the encoding on the previous slide were as many as the number of nodes in the network. And there is a lot of research on trying to find efficient encodings and for solving for subclasses of constraints that arise in these encodings. So in this work, we take an alternate approach where we consider network size reduction. That is, we try to reduce the size of the neural network so that we can get encodings which are smaller and thereby scale the analysis of these encoding-based approaches. Next, I will discuss an abstraction-based approach for neural network size reduction. This is a joint work with Zara, who is a PhD student, and this appeared in NeurIPS 2019. So the broad goal is to construct a smaller neural network, which we can use instead of the original neural network for the purpose of our analysis. That is, given a concrete neural network, we will construct an abstract neural network, which is potentially smaller. Now we can expect this abstract system to have the same input-output relation as that of the concrete system, but that would lead to very little reduction typically. Hence, we will relax the requirement and say that the smaller network has an input-output relation which over approximates the input-output relation of the given system. Now, note that the neural network is a deterministic system that is given any input, it has a unique output. Hence, if we consider a neural network for the abstract system as well, then the only way it will over approximate it is if it has the same input-output relation as that of the concrete system. Hence, we allow some flexibility and consider a slightly different data structure for the abstract system, in which we have some amount of non-determinism. More precisely, for a given input, the new data structure can now produce multiple outputs, and we refer to this new data structure as an interval neural network. It is very similar to a neural network, except that now the edge weights and the biases are intervals instead of just one particular weight. And the semantics is, again, very similar to a neural network, except that in each step, we can choose a value from the interval of these weights and biases to compute the valuations for the next layer. For instance, the value at this S11, S12 node can be the value at the node S01 times 1.5 plus the value at the node S02 times 4.5, which are in these corresponding intervals, and adding 19.5, which is a bias that is in the interval for the bias at this node. Note that now we can have multiple values at each node, and hence for a given input, the output eventually can be a set of output nodes. Another way to interpret this interval neural network is as a set of potentially infinitely many neural networks, each of which is obtained by instantiating the edge weights and biases to a value from the corresponding intervals. The broad approach to solving the output range analysis problem consists of two steps. In the first step, we consider an abstraction procedure that takes as input a neural network and outputs an interval neural network, which is potentially smaller and over approximates the input-output behavior of the neural network. And in the second step, we consider an MILP-based encoding of this interval neural network, which can then be used to do safety analysis. So the main questions that we need to answer are, how do we abstract the neural network into an interval neural network such that over approximation is preserved? And how do we encode the input-output relation of this interval neural network? Because the previous encoding that we showed was for a neural network where we had unique weights on the edges. Let's first look at abstracting the neural network to the interval neural network. The broad approach is to partition the nodes in each of the layers and merge them so as to form a smaller neural network. Now, the main question that we need to answer is, what should be the weights on the edges and the biases, or the interval weights on the edges and the biases, which will guarantee the over approximation? Okay, let's take a first try. We can take that to be the interval hull of the weights that on the edges that are being merged, or the biases that are being merged. That is, we look at all the weights on the edges which are being merged and take the range of those values to be the interval corresponding to the abstract edge. Let's look at an example. Consider this concrete system, and let's say we merge these two nodes in the center. We get this new abstract system where the first abstract edge has a weight of 1, because if you look at all the edges that are being merged, all of them have a value of 1. So the only value in the interval is going to be 1. And similarly, the second edge also has a value of 1. Now let's look at what happens if we give a value of input 1 to the first system, that is the concrete system. So we get a value of 1 at the node S11 because it has only one incoming edge. Similarly, we also get a value of 1 at S12. And this will lead to a value of 2 at the output node. So the value of 1 as input gives a value of 2 as the output. Now let's give the same input to the abstract system. We give a value of 1 to the input, we get a value of 1 at the second node, which will then lead to a value of 1 at the output. So here, a value of 1 at the input gave a value of 1 at the output. And note that both systems are deterministic, and the abstract system is not over approximating the concrete system. So input value of 1, output value of 2 is not a possibility in the abstract system. So what actually went wrong? What happened is that when we consider a value at a particular node, we are adding up the values at S11 and S12 weighted by the weight 1, right? When we merge, we actually forgot the information that there were 2 nodes that were being merged. And so that needs to be added twice towards this output. So the fix for this is essentially to scale the interval that we get, interval of values that we get, by a factor, which is the number of nodes that are being merged in the source of those edges. Okay, so in this particular case, since 2 nodes were merged, we're going to scale up this interval 1, which is a singleton interval, by 2. And so now we will see that we'll get a value of 2 at the output, and which is now going to have the pair input 1, output 2 that the concrete system has as well in the abstract system. We can show that this abstract interval neural network that is obtained by considering the interval hull of the edge weights and the biases and doing the appropriate scaling is going to be a sound abstraction of the given concrete neural network. More precisely, we can show that the input-output relation of this constructed interval neural network over approximates that of the neural network. And this is easy to see if we interpret the abstraction that is happening in each layer as happening in 2 steps. The first step where we consider the merging of the nodes on the left. Here, we need to consider the interval hull and scale it by a factor which corresponds to the number of nodes that are being merged. And this is needed because each of these nodes need to contribute once to the sum that is happening at the output node. On the other hand, the second step would be merging the nodes on the right. And here we merely need to collect the values that can appear on these output nodes. So a simple interval hull will do the job and we don't need to do any more scaling. So further details on this correctness of the abstraction can be found in the NeurIPS paper. One point to sort of make here is that the abstraction is going to be sound irrespective of the activation function that we're going to use. Now that we have seen how to abstract an interval neural network into a neural network, the next step towards solving the output range analysis problem is to encode this interval neural network as a mixed integer linear program. So let's recall how we did it in the context of neural networks. We constructed this formula, encoding of x's, which essentially encoded the input-output relation of the neural network. And then we optimized this variable x output that captured the values of this output node over these constraints of this encoding. And the max and min value of this x output gave us the range of the output values. The encoding excess essentially consisted of these constraints, which was basically the big M encoding. Note that now instead of a neural network, we have an interval neural network where the edge weights and the biases are intervals. That is, this weight and bias are no more single values, but they come from an interval. One straightforward way to extend this encoding to the setting of interval neural network is to treat these wi and bi as variables and add a constraint that these variables lie within the corresponding intervals. That is, we say that wi is going to lie within the lower and upper bound of its corresponding interval, and so does bi. Note that now we have this wi to be a variable. This constraint is no more linear because we're multiplying two variables. So we move from being a set of linear constraints and introduce some nonlinearity if we do the straightforward encoding. So we consider a slightly different encoding wherein we can still preserve the linearity. And it is based on the simple observation that we can construct an equivalent set of constraints corresponding to these nonlinear constraints by replacing the weights and biases by their corresponding upper and lower bounds in appropriate inequalities. More precisely, when this linear constraint appears as a lower bound, we can replace this wi and bi by the corresponding lower bound values. And in this linear inequality where the linear constraint appears as an upper bound, we replace the wi and bi by their upper bounds, wiu and biu. Now, to see that these two constraints capture equivalent set of assignments, consider an assignment for the nonlinear constraint. That is a valuation for xs and xs prime that satisfies these constraints. Note that if we replace this wi by a lower bound value, this constraint is still satisfied because this xs is a positive value. Okay. And the xs is always going to be positive because it is the result of the application of a ReLU function in the previous setting. So now let's consider an assignment for this linear constraint and show that it will also satisfy the nonlinear constraints. Suppose there is a value for xs and xs prime that satisfies these constraints. What we need to show then is that we are able to choose a value wi and bi in the interval between this lower and upper bounds, which also satisfies these constraints. And that is easy to see if we interpret this linear constraint or this linear expression as a function of these weights and biases. And then the intermediate value theorem gives us such a wi and bi which lies between these intervals. So what we've done so far is an abstraction procedure to abstract a neural network into an interval neural network. Note that that abstraction procedure applies irrespective of the activation function that is being used. And then we showed how to encode this interval neural network into an MILP, a constraint. And this particular operation is specific to the ReLU operation. However, note that we can use this abstraction procedure in conjunction with any other neural network analysis technique, as long as we can extend it to the setting of interval neural networks. And what we saw here is that it might not be too difficult to extend existing analysis techniques from the neural network setting to the interval neural network setting. Next, we present the results of the experimental evaluation for the abstraction-based analysis algorithm. We will consider ACAS-XU as the benchmark for doing the analysis. It is a neural network with 6 hidden layers and 50 neurons in each layer. Our abstraction algorithm is implemented in Python, and we use Gurobi as the backend MILP solver. And we will evaluate the effect of different granularity of abstraction on the verification time, as well as the precision of the computed output range. So on this graph, you see the number of abstract nodes on the x-axis, which is essentially the number of groups into which the neurons of a particular layer of the neural network are split into. And on the y-axis, you see abstraction time on the picture on the left, and encoding time, that is the time to construct the MILP constraints, which is depicted on the picture on the right. As you can see, the abstraction time and the encoding time increase as we have more and more abstract nodes. For each number of abstract nodes, we consider different random splittings. So you see three plots on each graph. The blue corresponds to the minimum time, the red to the maximum time, and the yellow to the average time taken by these random splittings. Though the abstraction and the encoding time increase with the number of abstract nodes. The absolute time taken is pretty small, less than a second. So this is not a bottleneck towards the overall analysis time. So here you see the number of abstract nodes plotted against the time it takes for the Gurubi to solve the MILP constraints. And the MILP solving time increases much more drastically than the abstraction or encoding time when we increase the number of abstract nodes. On the right, you see the output range computed. And as you can see, the output range becomes smaller and smaller. That is, it becomes more precise as the number of abstract nodes increases. And this is sort of expected because as the number of abstract nodes increases, the interval neural network is getting closer and closer to the actual neural network. As you can see, the time and the precision can vary quite a bit based on the particular partitioning that is considered in the abstraction, even if the number of abstract nodes, that is the number of groups, is the same. And so there is a lot of room for more experiments as well as heuristics to find good partitioning algorithms. To conclude, we considered the problem of safety analysis of AI-controlled cyber-physical systems. The safety analysis consisted of two primitive operations, namely the post-computation and the output range analysis. In order to efficiently compute the output range of a potentially large neural network, we considered abstraction-based analysis wherein we construct a small abstract system, which is an interval neural network, and do the analysis on this interval neural network. And we extended existing MILP-based encoding approaches to deal with the interval neural networks. Our abstraction-based approach complements existing approaches in that our abstraction applies to a general class of activation functions and can be used in conjunction with any of the existing techniques as long as we can extend those techniques to tackle the interval part of the interval neural network analysis. And our experiments highlight the trade-off between the precision and the computation time. However, we noted that the precision of the output range is affected not only by the size or the number of abstract nodes, but the specific choice of the partitioning that is used to construct those abstract nodes. Hence, we are currently exploring different partitioning strategies. And we are considering a cigar-based approach, that is a counterexample guided abstraction refinement-based approach, wherein we consider an execution in the abstract system that violates the safety spec to guide the choice of the partitions in the next iterations. We are also considering more complex activation functions, and we are analyzing the whole CPS with the neural network in the closed loop. You can find more details of the work that was presented here in the NeurIPS 2019 paper with Zara. I would also like to thank our sponsors who have supported this project, basically NSF and ONR. Thank you.